we label the change points as outliers if the mean returns to the previous value very quickly and the persistence score is low. And those scores are given in this fashion. So what we are doing is we are transforming the features. So once we have conducted the decafs, so these are some of the things that we have to calculate from there. So you have the delta mu v, or the mean difference, the persistence score. These are all calculated from all those things that we are estimating in the decafs, the AR1 model estimation. And based on these, we are forming certain vectors, delta mu s, phi, and v, which are then moving into, we are scaling them and putting them through a Fourier transform. And then we are using them recursively, almost like an LSTM, but not exactly, because there are no output gates, forget gates, input gates. But basically what we are doing is we are running them through a certain set of weights, and then through back propagation, we are also updating the weights as per the requirement. Also, these are some of the calculations that we have done to update the weights recursively. And this is the optimization function, or the loss function that we need to maximize. In this case, this is the payoff function that we need to maximize. We can also convert this. We can take an inverse and then minimize it, whatever we want. And then on the basis of that, we get a predicted value of whether or not the shift is going to recoil or it is going to sustain. And these are some of the algorithms that we have used. So I will not go through them as we have very limited time. Okay, so yeah. So for the performance evaluation metrics, we've used a penalized mean residual life index, where mean residual life is nothing but this 1 upon q, summation 1 over I running from 1 to q, absolute value between the tau I hat and tau I being the change point and tau I hat being the estimate of that change point. So how much, the more delay you have in estimating the change point, the higher will be your mean residual life. And if you take 1 by 8, the lower it is, basically the worse it is. So if you multiply that with the false positives, now you have the penalty element. So the more false positives your model is giving, your mean residual life will be affected by that, or basically the index that you're calculating will be affected by that. So then we have also calculated the empirical probability of misclassification, the classification accuracy, AUC, precision, recall, F1 score. Now, most of them we have seen there is a severe data imbalance, because we've used real life data sets to analyze. So we found that the F1 score and even the weighted precision, recall, and F1 score are probably better indicators of how good a model, the classification is being done, because as you know, there are not many change points that are being taken in by most of the models. So the resulting input vector, or the input data for that neural network is very small. So because of that constraint, and because of severe imbalance, because most of the models, they are not being able to classify that or label that, the required shifts are also very rare in nature. So because of that, we're getting a very low number of cases to enter into the neural network that have actually required shifts. So that is one problem that we have addressed here. So we have used 2 benchmark data sets. One is the well-logged data set.
Yes. You have 2 minutes.
Yes, sir. Almost done, sir. The well-logged data set, which is a canonical benchmark for change point detection across literature. And we have also used real-time Bitcoin price data from January 2018 from December 2024. Why Bitcoin? Because over the last few years, if we have gone through the news, anybody who is acquainted with financial news knows that the Bitcoin has been seeing abrupt shifts in its price starting from 2015 onwards. So, but again, due to computational constraints, we had to restrict ourselves to from January 2018 to 2024. If you have higher capable machine, you can even extend that backwards. We have retrieved that directly from Yahoo Finance, and a public code repository has been made at GitHub. So if anyone wants to check out the code, they can check it out here. And yes, so these are some of the parameter estimates that we have for the change point detection model, which is the penalized AR1 model that we're talking about. And we can see that the standard deviation of drift in the AR1 signal is 497, whereas that of the AR1 noise process is pretty high. So as you can see, as there is a lot of noise, much of it could be attributed to autocorrelation parameter, but we can see that the autocorrelation parameter estimate here is 0.14, which is very close to 0. So unfortunately, we expected that the data, in this case, we have done this on the well-log data, this might give us some severe autocorrelation, but it didn't happen. As you can see, our model performs better here. Yes. Here also, as you can see, our model fares better in all of the metrics. And this one is our model. As you can see, there are very few segmentations being done, whereas in the others, they are either very crowded or the fit is not very good. Okay, so this the earlier ones, this has been done on the Bitcoin dataset. This one has been done on the well-log dataset. And yes, these are some of the model benchmarks. Our proposed DCAPS FPNN framework, this includes autocorrelation, higher outlier concentrations, and transient versus sustained regime shifts as well, as we have seen. And it outperforms existing models across domains here. Now for class balancing and augmentation of rare shifts, we can also in future scope, we can use these also. And these are my references.
Thank you, Agnivadas. Thank you.
Thank you, sir.
Professor Ghosh and Jain.
Yes. Actually, since we are out of time, query I will ask.
Exactly. Yes, sir.
What is autocorrelation noise in your work?
Autocorrelated noise, sir, the error component that we had, if it is autocorrelated, then there are certain problems that are associated with change point detection. Sometimes there are delays in the change point. Let's say you have a change point detection framework and they are trying to predict whether or not tau I will be a change point. So if there is autocorrelation, there may be a chance that instead of tau I, you get 2-3 time steps ahead or 4 time steps ahead, which might not be suitable if accuracy is a concern.
Your error term is distributed normally with mean 0 and variance sigma square or sigma square I?
No, sir. That is sigma square. That is fixed. But because there are two error components, two noise components, one in the signal and one in the error in the noise itself. Because the noise itself is of the AR1 type.
But when there is a noise, say that variance may be sigma square omega, that is heteroscedasticity may present
Yes.
in that case.
Yes, sir. Yes.
So you are taking the homoscedastic case, na? So
yes.
Heteroscedasticity may come there also because you are taking the automatic noise you are taking.
Yes.
Okay, thank you.
Homoscedastic.
Time is not there, so thank you very much.
Yes.
Madam?
Sir, just a small query.
Yes, ma'am.
You were talking of MRL index.
Yes, ma'am. Pardon?
MRL, mean residual
mean
life
residual
index.
life. Yes.
There is a term, mean residual life in reliability as well.
Oh, I'm sorry, ma'am. I actually, this is a term that we thought we had developed for this particular case when there is a change point and we are estimating a change point and there is a gap. So basically, the higher the gap, we wanted to assign something for this metric.
So it has a different interpretation here.
Yes, ma'am.
Because there it has a different interpretation.
We will surely change the nomenclature if.
Yeah, you can check it.
Happening. Surely, ma'am. Yes.
Okay, thank you.
Thank you.
Well, Dr. Agnivadas, I noticed that the standard errors you computed for some estimates of the AR1 process, their magnitude is large in number.
Yes, sir. The standard error, no, sir. Yes, one second, sir.
So more than hundreds, 200s.
Yes, sir.
Thousands.
This one's the standard deviation of drift in the AR1 noise process. Yes, sir.
Yeah. So why? Can you tell me? Because the estimates for them, the standard deviation is too large.
Yes, sir. Because as I said, sir, the DCAPS model by itself is not prone to outliers. So that is the reason we are embedding it with the neural network, so that it.
Now, how reliable? When the standard deviation is too large, they could deviate much from the true value, right?
Yes, sir. But this
In
this
that case, how can the estimate could be reliable?
correct, sir. Correct, sir. But this estimate is only for one phase one, the phase one model, the air one model. YT equals
Sure.
mu t plus epsilon t. That
So
model.
you are not going to use these estimates?
Yes, yes. These are the estimates that are coming from that model only, sir. But
I understand. It
because
comes
of
from
this
the
problem, we are
model.
having
Okay.
to go for the neural network there.
No, what my question is, you are
Yes.
applying a process to compute an estimate, and the estimate yields a larger standard deviation or
Yes.
standard error. In
Yes.
fact, correct is standard error.
Yes, sir.
How reliable an estimate which has a large standard error? Okay,
Yes.
right. Thank you. Think over it. Thank you.
Yes, sir. Thank you, sir.
Right. Our next contestant is Dr. Gaurav Kanpal.
Yes, sir.
Please share your
Am I audible,
screen.
sir? Yes, sir. I'm sharing my
Yes,
screen.
you are audible.
So my screen visible?
Yes, visible. You can make it in full screen. Now it is very visible.
Is it fine, sir? Okay, good evening, everyone. My name is Gaurav Kantpal, and I am a third-year research scholar in Department of Mathematics, IIT Kharagpur, and I'm doing my research work under the supervision of Dr. Nitin Gupta. And the title of my presentation is Testing Generalized Pareto Distribution Using Extropy and Steen's Identity. This is the outline of my project, of my presentation. First, I will introduce some basic definitions and CDF and PDF of generalized Pareto distribution. Then I will tell you two characterizations which we have proposed for generalized Pareto distribution. And after that, using this characterization, we have given goodness of fit test for generalized Pareto distribution. And then we have taken a real world data set where we have used our goodness of fit test. And finally, I will conclude the giving the conclusion. So this is the first slide. As you can see, in equation number 1 and equation number 2, we have given cumulative distribution function and probability density function of generalized Pareto distribution. And if you'll carefully see, we have two parameters here, theta and beta. So theta is actually scale parameter, which will be always positive, and beta is actually shape parameter, which can be positive or negative. Why I'm particularly focusing on shape parameter beta, because if you'll see, I have written below the equation number 2 that for beta positive, support is positive x-axis, and for beta negative, we have a bounded support here for generalized Pareto distribution. So based on the shape parameter, actually the support is varying. So that is why this distribution, to creating a goodness of fit test for this distribution is kind of a challenge. And this is on GPT has very good properties also. As you can see in the note, the first property is exponential distribution is a limiting case of generalized Pareto distribution when beta is tending to 0. And second one is when beta is equal to -1, this distribution is actually uniform 0, theta distribution. And third very interesting property it has, like if x is following generalized Pareto distribution theta comma beta, then xt, which is an x's age after a given age t, which is x minus t given x is greater than 3, will be a generalized Pareto distribution again with some different parameter as theta minus beta t comma beta. So this implies that if this model is consistent with a set of data for a given threshold, then it must be consistent with all the higher threshold. And these are some areas where we actually see, people actually see that the generalized Pareto distribution is coming into play. The first one is for modeling financial risk, like market crash, large fluctuation in asset prices and all. And the other one is to model extreme weather events like extreme rainfall, extreme wind speed, and some other weather phenomenon. And it has been also come in picture when we are calculating value at risk for risk management and for modeling large insurance claims also. So the question here is people generally assume that the data which is coming from such kind of areas are generally generalized Pareto distribution. So does every data from such an area follow generalized Pareto distribution? That is the question. And can we always assume without checking it? So the answer is no, we have to check it. And the answer is to check it, we need goodness of fit test. And to provide a goodness of fit test, we have given two characterization, which is the first characterization is based on dynamic survival extropy, and the second one is based on Steen type identity. So I will start with dynamic survival extropy. So in 2020 and 2021, Sathan and I provided a definition of dynamic survival extropy in his paper. and he has given the formula as you can see in JSXT, which is minus half integration t to infinity f bar x divided by f bar t ka whole square. And as you can see, this is a function of t now. So that is why that is the dynamic part here. That is the time part. And they have also given two classes, which is a very new classes for the literature, which is increasing dynamics of exotropy class and decreasing dynamics of exotropy class. And to check like particular distribution is following is coming under one class, they have given this theorem, which you can see as theorem number 1. So the theorem says the distribution f is in increasing dynamics of exotropy class if and only if this particular product of dynamics of exotropy and hazard rate function is more than -1/4 or less than -1/4 for all t. So to check, we need this product, and when we actually see this product, like our characterization is based on this product only, which I will show you in next slide. This is as you can see in theorem number 2, what we have got, like let f be a distribution function with hazard rate hft, then f is generalized Pareto distribution if and only if this product of dynamics of exotropy and hazard rate function is constant. So as you can see here, these two functions are function of t, but if the product is constant, then we will say that this distribution is generalized Pareto distribution, and we have a proof of this theorem in our paper. Further, we have another characterization which is based on stream type identity. So as you can see in theorem number 3, we have another characterization as let x be a positive value random variable with cumulative distribution function f. Then x is generalized Pareto distribution with PDF as given in the previous slides. If and only if the distribution function of x has a form as given in equation number 4, which is ft will be some expectation of beta plus 1 divided by theta plus beta x into minimum of x comma t. So why this characterization is very new? Because like there is a large number of characterization given by Bech and Ibner in 2021 paper, where he constructed characterization identities for absolute continuous univariate distribution. But the characterization which is he has provided, that is for the bounded support or semi-bounded support or real support. But he didn't give any characterization for a varying support, which is a particular case here for generalized Pareto distribution. So for that purpose, this is kind of a new characterization which we have provided. Further, using these two characterizations, we have given our goodness of fit test. So let's say x1 to xn be a random sample from the distribution f, which is defined on positive real numbers. Then we are interested to test the hypothesis, which is the null hypothesis f is generalized Pareto distribution. And alternative hypothesis, we have given two cases. One is for the positive part and one is for the negative part. So for the positive part, we have used stream type identity, and for the negative parts, we have used dynamics level exotropy characterization. So the first case, we will reject the null hypothesis if any of the alternative hypothesis is true, and we will not reject the null hypothesis if both the alternative hypotheses are not true. So further, for case 1, the positive shape parameter case, we have used type identity characterization, and we have introduced Kramer von Mises type test statistics. Like what kind of test is this? Like it is just a difference between two expression of cumulative distribution function, and we are taking square of it, and finally we are taking the integration. So we are actually summing up all the differences between two expression of cumulative distribution function. So further, using the Fubini theorem and some other theorem, we have given we got a simple expression as given in the last line of our test statistics, which is beta plus 1 square expectation of some expression and minus beta plus 1 expectation of some expression plus 1/3. Further, to estimate this, we use U statistics theory, and we consider the U statistic defined by UP, as you can see, and we have two symmetric kernels here, H1 and H2. And finally, our test statistic is given by equation number 8, which is in blue color, which is del hat P. Here, beta hat and theta are consistent estimator of beta and theta. And the test is to reject H0 in favor of H1P for larger values of del hat P. Further, for the second case, which is a negative shape parameter case, we use dynamics of exotropy characterization, and the equation number 9 is a part of that theorem, where if x is following generalized Pareto distribution, delta x will be 0, and otherwise it will be away from 0. So, and k is the proportionality constant given in the theorem number 2, which I showed you. And based on this only, we define a measure of departure, which is delta n, which is integration of delta x from, as you can see here, our integration is from 0 to minus theta by beta, because I said it earlier that for negative shape parameter case, we have a bounded support. which is from 0 to minus theta by beta. And further, using Fibonacci theorem and simplified further, we found out this delta n has a very simple expression. As you can see, 1/3 expectation of some very basic mathematical functions, which is minimum or addition and product. So further, we use again the U statistic theory to estimate this test statistics, and we find out that del hat n, which is given as the expression number 10, and where G is defined like this, and G is a symmetric kernel, and K hat is actually an estimator of K. And further, the final test statistic is actually to make the test scale invariant, we divided this del n by the scale parameter theta, and the final test statistic is given in blue color in equation number 11, which you can see is del hat star n, and therefore the test is to reject the null hypothesis H naught in favor of alternative hypothesis for larger values of modulus of del hat m star. So further, like as you saw that we have used the U statistic theory to provide the test. So using the central limit theorems of U statistics and asymptotic theory of U statistics, we have asymptotic properties also. And as you can see in these two theorems, the first one is like if you are considering beta hat and theta hat to be consistent estimator of beta and theta, then your del hat p and del hat n, which are that those will also be the consistent estimator for del p and del n. And further, we have an asymptotic normality condition here, as you can see in equation number 12. In the another theorem, which is let beta hat and theta hat be consistent estimator of beta and theta, then the distribution of under root n del hat p minus del p converges to a normal random variable with mean 0 and variance 9 sigma square. And sigma square can be obtained using equation number 12, where h has an expression given in the last line. And further, under H naught, we can actually we are actually getting our asymptotic normality, and using that asymptotic normality, this asymptotic test is given in equation number 13, where we are rejecting the null hypothesis H naught in favor of alternative hypothesis H1 P as significance level alpha if under root n del hat p divided by 3 sigma hat naught is more than Z alpha, where Z alpha is actually the upper alpha percentile of standard normal distribution. And similarly, we can find out asymptotic distribution for negative case also, because that test statistics is also based on U statistics. Further, the parameter estimation part actually, generalized spectral distribution has a problem of existence of this basic estimation techniques like this MLE and MMR does not exist for all values of beta. So that is a problem there. So Elva and Estrada provided two new estimator, which is namely asymptotic maximum likelihood estimator and a combination of maximum likelihood estimator and method of moment estimator. So we have also used the same parameter for our simulation purpose. And the first one, as you can see, equation number 14 and 15, those are actually asymptotic maximum likelihood estimator for beta and theta. And further, in equation number 16 and 17, these two parameters are actually combination of maximum likelihood and method of moment estimators. And actually these two... yes, sir. Okay, sir. These two estimators actually exist for all values of beta. Further, to provide the power of test, we have taken two special cases for beta equal to 0, which is the exponential case, and for beta equal to minus, which is the uniform case. And as you can see, we have taken a large number of alternative distribution from beta, V-bool, gamma, generalized gamma, absolute normal, Gumbel, chi-square. These are alternative distribution which we have taken. As you can see, the power we are getting is quite good, and the power is also increasing if you increase the sample size. These all powers are taking under a significance level of 0.05. And so further, we have actually taken a real life example. So this is the data of ozone level excess of Delhi, India, from June 2015 to November 2017. And this data is provided by Center Pollution Control Board, Government of India. So these kind of excess data generally actually follows the generalized spectral distribution. That is a kind of a assumption. So we have checked our goodness of fit test over it. So why such data is necessary? Because studying ozone level, which is exceeding 100 microgram per meter cube, is actually hazardous for our health, which is according to WHO guidelines. So that is why this data is kind of interesting to check, like whether it is following generalized spectral distribution or not. So as you can see, the total number of data which we are taking is the number of data is 108 data points we have here, and del hat star n value we are getting 0.02. And for 99% confidence level, actually we cannot reject the null hypothesis H0, and I have given critical value and other estimate the value of test that is in the red color. And we have checked this data using Kolmogorov test also, and Anderson-Darling and chi-square test, and none of these three tests reject the null hypothesis when a negative shape parameter is present. So it is kind of so we also cannot reject the null hypothesis for this particular data. And finally, to conclude my presentation, I am giving the conclusion here, which is we have provided characterization based on string type entity, and which is also applicable for GPT with a varying support. And second thing, we have provided dynamic subextropic characterization, which is new in literature. Third, based on these two characterization, we have given goodness of fit test, particularly for beta positive and beta negative case. And as I showed you, that our test is comparatively simpler than the classical test, Kolmogorov and Anderson-Darling test. And next point is our test has high power and asymptotic normality. And at last, I have applied this test to real life example of Delhi ozone level access data. Thank you.
Very good. Thank you, Dr. Gaurav Kalpal. Now the floor is open for interaction. Sir, Professor Ghosh, Madam Kanchan Jain.
Thank you, Dr. Gaurav. Good presentation. I have just one query, not the question.
Okay,
For the generalized Pareto distribution, by defining, you have taken when x is greater than 0, beta is greater than 0, and when x lies between two values, beta is negative, less than 0.
yes, sir.
But for goodness of fit and for power of test,
Yes, sir.
you have taken alternate hypothesis beta is greater than equal to 0. Equal to you have taken, and other beta is less than 0.
Yes, sir.
But while defining the PDF, you have not taken beta equal to 0.
Yes, sir. Actually, exponential distribution is a limiting case of that. But like while like if you are simulating it, so it is giving exponential distribution while simulation also. Like so in some literature, it is giving as limiting case, and some distribution is defined like for beta not equal to 0, the expression is as 1, and for beta equal to 0, the expression is actually equal to exponential distribution expression. So,
Second one more query was there,
yes,
that
sir.
we have taken that one theory that square root of n into delta p estimate minus delta p that
Yes.
follows normal distribution mean 0 and mean 9 sigma square.
Yes, sir.
This is not surprising. 9 sigma square, it is exactly getting.
Sir, actually, this is from asymptotic theory of U statistics. Like, if your test statistics have, let's say, k number of samples, like which it is taking. If you'll check in the test statistics part, so it is coming up x1, x2, and x3 for h1 and h2. Like we need 3 number of data here. So that time it will be like, let's say we need k number of data. So based on the asymptotic theory of U statistics, here it will come as k square sigma square, that kind of variance it will come. So it is from that theorem only. Like I don't know the proof of that theorem, but that is from the theorem itself.
Okay, thank you.
Yes, sir.
Madam?
Okay. Anji, Mr. Gaurav,
Yes, ma'am.
you were talking of this theorem about asymptotic normality.
Yes, ma'am.
So you just used that result, or did you prove it theoretically?
I have proved it, ma'am, but I did not prove. I used it using the asymptotic theory and central limit theorem of U statistics. Actually, the good part of our test is statistics is based on only U statistics estimators. So, and there is already theory for asymptotic theory for U statistic estimators. So we have used that to prove our asymptotic theory.
But
So
when you proved that,
yeah.
you said that you don't know how did you get that variance?
No, ma'am, I did not know like how in the actual asymptotic theory of U statistics they got the variance as k square sigma square from the number of samples.
Okay.
Like here I know like how I did. I use that particular theorem.
Because k is 3, so that's why 9.
Yes, yes, ma'am.
3 observations you are taking.
Yes, ma'am. 3 observation we need to calculate. So in this case,
And moreover, in your real life data, you have taken up to 17 Delhi level, ozone level. 2017.
yes, ma'am.
was the data not available after this?
Ma'am, actually, when I was collecting the data from this Central Persian Government Board, actually the data is in the cubes. Like you will have to write every, you have to open every page and you will have to write a data. But this data from June 2015 to November 2017, I got from GitHub. So there, somebody has already compiled this data, like from the website only. So
But
that
you
was,
can compile and get more data.
yeah, that I could have done.
Okay.
Yes.
Thank you. Nice presentation. Thank
Thank
you.
you.
Thank you, madam. Dr. Gaurav, you were discussing about the power of the test with
Yes, sir.
various competing distributions, more than 10 distributions you have considered it.
Yes, sir.
And under two cases, exponential case and uniform case. What makes
Yes,
the
sir.
necessity, what makes to carry out that such kind of a comparison?
Sir, actually, we have taken power analysis for other beta values
Two
also.
distributions are on one side and symmetric are also considered.
So these alternative distributions which were taken here, those are actually defined on the positive x-axis. So we wanted some other distribution which are actually defined on positive x-axis. Second thing, for a particular beta case, like we are taking beta equal to 0 and beta equal to -1 for this presentation only because these are very familiar distribution for the audience. Like in our actual paper, we have taken other beta values also for power analysis. There also we are getting the similar
No,
result.
I think
Power
you
is
don't
good.
get the point. The
Sorry.
power of the in the study of power of the test, you considered more than 10 distributions.
Yes,
Isn't
sir.
it? And under two different cases, exponential case and uniform case.
Yes, sir. So what I need to answer here, like
No, no. What is the purpose of carrying out? What is the purpose of conducting such a computation of the power of the test for two different cases, exponential case and uniform case?
so like let's say you have a goodness of fit test for exponential distribution. There are so many methods for there are so many goodness of fit tests for exponential. Like if you have a new method here for using some new concept of extropy and all, so we just need to check like how our test is better than other goodness of fit tests which are for exponential distribution. So for that purpose also our test can work there. So that is the reason why I have taken these two particular parameters. And similarly, there are some other goodness of fit
Do
tests.
you keep the
Uniform.
data distribution and other things? Do you keep the distance?
Sorry, sir, I did
Okay,
not.
right. Thank you.
Okay, sir.
Thank you. Thank you.
Thank you so much, sir.
You can close your screen. You can close your screen. Thank you. Thank you.
Yes.
Thank you. Sir, Professor Ghosh and Madam
Yes.
Kanchan Jain, all the 9 contestants have completed their presentations. We also interacted and we also made some observations.
Yes,
Based
sir.
on that, we can give our inputs, we can give our scores to that. We can share our scores among ourselves and we can present it to them. Before that, let us all congratulate all the 9 contestants for
Yes.
making the session this evening very interesting and informative. And all of them have done. On behalf of the jury board, we congratulate all the contestants for your sincere efforts. And all papers are very good. And based on the criteria, based on the parameters we are given with, we will assess your presentations and we will give our inputs to the organizers to come up with a final result. And I thank on behalf of the jury board, I thank all the contestants for your cooperation. Thank you. And it is for the organizers, Sir Professor Satish Kumar sir, Madam Shobha Nair, and it is a thanks from the jury board to you and Professor Satish Kumar for giving us this nice opportunity. And we will give our scores to you through mail.
Thank you, sir, and congratulations
sir.
to all the participants. Thank you.
And it is my duty. It is my duty to thank my colleague friends, Professor Ghosh and Madam Kanchan Jain, for keeping the sessions very, very vibrant and very, very and of course it is very, very alive. And thank you for
Give
interesting
congratulations
questions.
to Loganathan
Learned
by
something. Thank
conducting
you
very
very much.
nicely, smoothly, and timely
Sir,
this presentations. So you are really thankful to you.
it is all because of your cooperation
Thank you,
and the
thank you.
contestants also.
Yeah.
Thank you, sir.
So, Professor Loganathan, sir, Professor Ghosh, and Professor Kanchan Jain, ma'am. Actually, we are deeply indebted to all three of you for wonderfully conducting this competition. Actually, it was conducted on time without any. I think the participants would also have noted the way in which the competition went. So, on from our side, from the side of WSTA 2025 as well as ISF, we would like to express our heartfelt gratitude to each and every one of you, all three of you, for being with us in this process and for helping us out and for cooperating with us and for your support, sir. Thank you for the Thank you to the convener, Dr. Professor Loganathan, sir, and the jury members, Professor Ghosh.
We should ask the presenter to close their video because some their site is open. Can you request them to close their sites?
Yeah, okay. Dear participants, please close your presentations, okay? But I'm not. It's not visible, sir. I think they have closed it. But if anybody has kept it open, please stop sharing.
Dr. Satya Misra's site is open.
Oh, okay. Please take care of that. And to the participants, all of you had done wonderfully well, and I'm sure it's a tight competition. Just we wish you all the best, and we can wait for maybe we can Loganathan, sir, we can publish the results within maybe 10 to 15 days. No, sir.
Certainly,
There is
madam. I will discuss with Professor Ghosh and Professor Kanchan
Sure,
Jain,
sir.
and
Sure, sir.
we will finalize it and we will inform you.
So we
Yeah.
shall submit tomorrow.
Yeah, you can have a
Yes.
discussion and decide among yourselves, sir. It is your call. And now, Professor Satish Kumar, sir, please join us and put in a few words.
Yeah, in fact,
And sir, I think Professor Satish Kumar, sir, I think
Yes.
we can ask the contestants to leave the meeting so that we can have discussions, right, sir?
yeah. Okay.
Yeah.
Professor
So,
Satish, sir?
I think the jury
Thank you,
members
contestants,
to discuss and finalize tomorrow or day after, according to your convenience.
Then tomorrow we can submit. Don't look for tomorrow morning.
yeah,
we can submit.
okay.
Okay.
Okay, sir. That would be great.
No, sir.
Yeah.
The thing is,
Tomorrow early morning we'll submit.
I think Loganathan, sir, is saying something. Please say, Professor.
So, in case the confidentially in things speaking, I think they are.
There are still participants.
Yes. Dear participants, can you please log out because actually some on the discussions are to be done, official discussions. So we are requesting you to please log out. Your results will be announced as soon as possible. Thank you for your cooperation. I think 2 of them are still there.
3.
Yeah. That's our
Yeah.
students.
sir, Professor Satish Kumar, sir, shall we submit each of us? Shall we submit the scores each of us to you so that you will compile and prepare a consolidated statement, or?
Anyway, Professor, it's better you can, Professor, you have to consolidate and come give the final.
Students.
Without including we people, it's better all the reports has to you collect and consolidate.
Whatever you
Satish sir,
decide.
excuse me, Satish sir. Can you please can we please exit those 2 or 3 participants who are still there, because can you please ask Nikhil to exit them so that I think they are not there anymore. They have just kept it open and gone.
Just a minute.
Yeah.
Because they are showing 8 participants are showing.
Yes. Yeah. Actually 2 students are there. The remaining are Asuli,
Nitya
Sandhya, and
and
Nitya.
Sandhya and Nitya.
Yeah. Okay.
Nitya is here.
Nitya also.
or if Professor Ghosh and Professor Madam Kanchanchain, if they send their scores to me, I will consolidate and I will also share with them, and we will
Okay.
finalize it, and we can submit to Professor Satish Kumar or otherwise.
Okay, sir.
Yeah, that will be fine, sir. That'll be better. Thank you.
Ma'am,
That-
is there
that-
any cap?
Professor,
Pardon?
Is
Madam?
there any cap on the marks?
No, no, ma'am.